Hi everyone! Today we're going to continue discussing reactions and reaction rates. So last time we saw how to calculate a reaction rate based on concentration and time. So today let's start by discussing how reactions occur. So an explanation of how reactions occur is called a reaction mechanism. And a reaction mechanism is often expressed as a number of processes that must take place for reactions to occur. So down below we have a few assumptions for how a reaction occurs. So for assumption 1, we're assuming that reactant particles must collide with one another in order for a reaction to occur. So let's say we have a reaction between A and B, and they're going to form some product, C. So we have a combination reaction there. Now again, according to assumption 1, A and B are not going to react if they're far apart from each other. They actually need to collide with each other in order to react. And that makes sense, right? Now, assumption 2 says that reactant particles must collide with at least a certain total energy if the collision is to result in a reaction. Okay, so A and B then, they can't just, touch each other. They actually have to collide with enough energy or force in order to actually react. And then assumption 3, in some cases, colliding reactant particles must be oriented in a specific way if a reaction is to occur. So let's look at an example where that is true. So on this slide, we have a depiction of what's called collision theory. So our example here involves the reaction of carbon monoxide and oxygen to produce carbon dioxide. And everything here is a gas, but I'm going to leave out the states just because I don't have enough room there. Now this is not a balanced equation just yet. So on both sides of that equation, we do have one carbon atom. But on the left-hand side, we have 3 total oxygens, and on the right-hand side, we only have 2 oxygen atoms. So whenever you have an odd number of atoms on one side, it might be easier to start by doubling the number of oxygens or doubling one of the molecules. So I'm going to double the carbon monoxide molecule, just so we have an even number of oxygens on the left-hand side. All right, so now we have 4 oxygens on the left and only 2 on the right. So let's double the number of oxygens on the right. And we're also doubling the number of carbons, which matches what's on the left. So we have a balanced equation. Now, there are a few different ways that carbon monoxide can collide with or interact with oxygen. However, in order to get our product, we want carbon to end up with 2 oxygens at the end instead of just 1. So carbon is probably going to need to interact with another oxygen. And remember, our Lewis structure for carbon dioxide looks like this. So we definitely want carbon to grab onto another oxygen. So in our first example, carbon monoxide is colliding with oxygen, but 2 oxygen atoms are facing each other from each molecule. So that's not going to result in our desired product because carbon is not interacting with another oxygen there. So no reaction occurs there. But then down below, carbon monoxide is again interacting with oxygen, and the carbon atom is facing an oxygen atom from the oxygen molecule. So now that carbon can grab onto an oxygen and we'll end up with carbon dioxide. So that does result in a reaction. So again, if we go back to assumption 3, in some cases, colliding reactant particles must be oriented in a specific way, or they have to be facing a particular side of a molecule in order to interact. All right. So again, orientation effects are related to which side or end of a reacting particle is actually in contact with another particle during a collision. So sometimes this isn't very important. For instance, let's say that we have calcium ions and carbonate ions. So calcium as an ion is just a single atom with a charge, so it's spherical in shape. And then the carbonate polyatomic ion looks like this. So it is trigonal planar. And it kind of has a spherical shape as well, and then an overall -2 charge. So if your molecules or ions are spherical, it doesn't really matter which way they're facing, or which part of one molecule attacks another molecule, because they are spherical, so their orientation will be the same regardless. And then once these two ions interact, they form calcium carbonate, which is insoluble and settles out of the solution. So this would form a precipitate. Now, orientation effects do become important when the reacting particles are not spherical, as in the following hypothetical reaction. So in this reaction, we have molecules A, B, and C, D. And in the end, we're trying to form AC and BD. So what we want to happen is for A to line up with C, and we want B to line up with D so that they can interact and form our products. So on the right-hand side, we have a few different possible ways that these molecules could interact with each other. So A, we have something called a favorable orientation. So A is lined up with C and B is lined up with D. So those two molecules are parallel to each other, and once they collide with enough energy, they can form our new products. However, in figure B, again, the molecules are parallel. However, A is lined up with D, which is not one of our products. And B is lined up with C, which also is not one of our products. So that would be an unfavorable orientation. And then in figure C, B is lined up with D. So that could potentially form a product that we want. But A and C are really far apart from each other. So unfortunately, in that case, we have another unfavorable orientation because A and C won't form the other product. So in some cases, orientation doesn't matter, and in some cases, it really does matter. It just depends on the reaction and what you're trying to form. So we saw from our assumptions that molecules have to collide with a certain amount of energy, and sometimes we have to add some energy for a reaction to start. So for many stable mixtures, the addition of a small amount of energy starts the reaction, which then continues without the addition of any more stimulus or energy from an outside source. So that small amount of outside energy that's needed to start a spontaneous process is called the activation energy. So down below, we have an energy diagram. And on the y-axis for this diagram, we have increasing energy. So it's increasing going up the y-axis. And on the x-axis, we have the progress of the reaction. All right, so first we start out with our reactants. And our reactants have a particular energy, so they're kind of high in energy here. And then they need a certain amount of energy in order to react with each other. So they need to actually gain some energy. So they need to get up here in energy in order to react. And the difference between that energy at the top and the reactants energy when they're just kind of hanging out, that is our activation energy. Then once the reactants hit that activation energy and react, they kind of gently fall down this energy slope. So they decrease in energy and we end up with our products, which in this case have a lower energy than the reactants. Now what's also cool about this type of diagram, the energy difference between the reactants and the products, that's the energy that will be released by the reaction. So if energy is released, is that exothermic or endothermic? Exothermic, because it's external, right? So this would be an exothermic reaction. So energy diagrams can be pretty useful because we can figure out or plot how much energy is needed to get the reaction going, and then also how much energy will be released at the end, at least for an exothermic reaction. We'll talk about endothermic reactions in a bit. So an example of a reaction that needs activation energy is just an ordinary match. So with matches, you need to apply some friction before it will light. And that is work, which is a form of energy. So the energy of rubbing the match is the activation energy needed to cause the match to react and the match to ignite. So the reactants on the tip of this match, you know, if a match is just sitting out, it's not going to spontaneously combust. We do need to provide that friction to get it going. So that's the activation energy. Then once the match is ignited, it will react with oxygen in the air until the reactants run out. So once we get the reaction going, it does burn spontaneously, and eventually we end up with our products. All right, now some reactions have a really high activation energy, and some reactions have a really low activation energy. So there are a couple of different examples here showing the different amounts of activation energy that are necessary. So on the left, we have a reaction where 4 moles of phosphorus react with 5 moles of oxygen molecules. And this reaction doesn't require a lot of energy. So the activation energy is really, really low. And then at the end of the reaction, we get P4O10 as our product. Now you'll also notice that the difference in the energy levels of the reactants and products is really high. So we end up with quite a bit of energy that is released from this reaction. So 720 kilocalories of energy. So usually when you have a lot of energy that's released, or you have a huge energy difference between your reactants and products, it's because the reactants are really unstable. So they're really high in energy. It's kind of like if you consume too much coffee or too much sugar, you probably feel really shaky and really unstable. But then once that leaves your system, you feel much better. You feel a little more stable, a little more relaxed. And that's kind of what's happening here. So the initial reactants are super high in energy, super unstable. But then once they react with each other, they become something that is much more stable. So it's much lower in energy. And that's the P4O10 product. Now on the right-hand side, we have a reaction between sulfur and oxygen, and this requires a lot of energy to get started. So this is a huge barrier that those reactants have to get over. And then at the end, we get sulfur dioxide, which again is lower in energy than the reactants. However, in this case, the reactants and the products are both fairly stable, so they're pretty close in energy to each other. But that's also why the reactants need a lot of energy to get started, because they're pretty stable on their own. So why would they want to react if they're already stable? So that's where we would need to give them a push. It's kind of like if two single people, they're pretty happy on their own. They don't really need to date anyone or get married. But maybe they need that push from their friends to say, hey, you guys would be perfect together, get together. So sulfur and oxygen, they kind of need a little push to react with each other. So because the reactants and the products are so close in energy, that reaction will only produce a small amount of energy at the end. So it's only going to produce or release 71 kilocalories of energy. All right, so let's talk about endothermic reactions, because we already talked about a lot of different exothermic examples, but some reactions are endothermic. So down below, we have an exothermic energy diagram on the left, and then an endothermic energy diagram on the right. And you'll notice that they're kind of flipped. They're sort of the inverse of each other. So in an exothermic reaction, the reactants are higher in energy than the products. And then for an endothermic reaction, the reactants are lower in energy than the products. So they're flipped here. So we've already seen quite a few examples of exothermic reactions, and we saw that the energy difference between the reactants and products is equal to the energy that is released by the reaction. So that could be in the form of heat, for instance. And then for an endothermic reaction, we can still take the energy difference between the reactants and products, but this time that will be equal to the energy that is absorbed by the reaction overall. So in our exothermic example, if we look at the difference between the top of that hill and the reactant energy, it's pretty small. The activation energy isn't so bad. But if we look at the endothermic reaction and take that same difference between the top of the hill and the reactants, that's a huge activation energy. So overall, that reaction needs a lot of energy to occur. So, so that would be overall an endothermic reaction. All right, so hopefully that helps a little bit with kind of seeing the differences between energy diagrams for exothermic versus endothermic reactions. So now let's talk about some factors that influence the speed of a reaction, or the reaction rate. So last time we did talk about a couple of factors very briefly. We mentioned concentration and temperature. But there are a few other factors that can influence how quickly a reaction proceeds. So one of those factors is the nature of the reactants. So we'll talk about that in a second. And again, concentration and temperature. And then the last factor is the presence of catalysts or inhibitors. So down below we have an example of glow sticks. When I was younger, a lot of the time people would have their birthday parties at a roller skating rink, and we would get glow sticks. And as soon as I got home, I'd put them in the freezer because I had been told that that would make the glow sticks last longer. And I didn't really understand why when I was a kid, but now it makes sense because I know that temperature can affect the rate of a reaction. So by putting glow sticks into a cold environment, we're slowing down or decreasing the amount of energy that the reactants have. So they're not going to be able to react with each other as well. So if we cool down the reactants, then they won't react. And that's going to decrease the rate of the reaction. So in the pictures below, we have a warm water bath on the left, and you'll notice that the glow sticks are glowing very, very brightly. And there's also a couple of glow sticks shown at room temperature for comparison. And then on the right-hand side, we have a cold water bath. And you'll notice that the glow sticks in the cold water bath are not glowing at all. So they're not reacting. So as temperature decreases, the rate of the reaction decreases. All right, so let's talk about that first factor. All right, so the nature of the reactants. Now, some reactants are just naturally going to react based on whether, for instance, they're charged, or if a reactant is really complex, it might not react that well or that easily because it is so complex, and maybe you need a very small portion of that reactant to react. So for instance, let's say we had a huge molecule and then we only needed this small part of the molecule to react with another molecule. That would be really difficult to achieve, right? So one example for the nature of the reactants, oppositely charged ions in solution will react pretty well together pretty quickly, and that's because the ions are strongly attracted to each other because of their opposite electrical charges. So down below we have a figure of a precipitation reaction, which we've seen before. And earlier we talked about calcium and carbonate and how they form a precipitate in solution. And again, that's due to the fact that they are very attracted to each other through their electrical charges. Now, what if calcium was trying to bond with nitrate instead? So we know from our solubility rules that nitrate is always soluble. And that's just the nature of that polyatomic ion. So in solution, calcium and nitrate won't react with each other. And again, that's due to the nature of the reactants. Now the next factor is concentration. So the reaction rate will generally increase as the concentration of reactants increases. And I have a video here showing that concept, so let's see if it works. So that was a very soothing video. I like the music. So this is a reaction that we saw in a previous lab where magnesium and hydrochloric acid react to produce magnesium chloride and hydrogen gas. And in the test tube on the left, so test tube A, that had dilute hydrochloric acid. And the test tube on the right, test tube B, had more concentrated hydrochloric acid. So with more hydrochloric acid molecules present, they can react more quickly with magnesium and break it down. So again, concentration of reactants can affect the reaction rate. Now we also said that temperature can affect reaction rate. So an increase in temperature corresponds to an increase in the velocity or speed and the kinetic energy of the molecules. So an increase in velocity will increase the number of molecular collisions that take place in a fixed amount of time. So that's similar to our reaction rate. Now we already talked about the example of the glow sticks, but I have another example of how temperature affects reaction rate.
Chemical reactions happen faster at higher temperatures because the individual molecules are going faster and therefore causing more collisions. For this experiment, you're going to need 2 glasses of the water. The glass of water on your left is hot water. I heated it in the microwave for a minute. The glass on your right is cold water, just ice water. You'll also need 2 effervescent tablets. We're going to drop the tablets in the glasses. Which do you think is going to react faster? The one on your left, which is hot, or the one on your right, which is cold? As you can see, the one on the left is reacting much faster. It's the hot water. It's almost done dissolving at this point. The one on the right is cold water. You can see down at the bottom of the glass, the tablet is still dissolving. And the one on the left is just about completely done at this point. The one on the right is still reacting. So clearly, higher temperature makes a difference.
Okay, so in that video, the glass on the left was hotter or warmer than the glass on the right. And when he dropped in those effervescent tablets, the one on the left reacted faster just due to the fact that higher temperature means more energy, which means more collisions. Now, the last factor is the presence of catalysts. So what are catalysts? Catalysts are substances that speed up chemical reactions without being used up in the reaction. Now, there are 2 different types of catalysts. One is called a homogeneous catalyst. So that's a substance that is distributed uniformly throughout a reaction mixture. So for instance, maybe you have a solution, so it's liquid, and you add a catalyst that's also in the form of a liquid. So the catalyst would have the same state of matter as the reaction mixture. And then there are heterogeneous catalysts, which are substances that are typically solids, and they have a large surface area so that the reactions can take place on that surface. Now, one example of a catalyst is something called an enzyme. So enzymes are a type of protein. We have a lot of enzymes in our bodies, and they're helping to break down food or other molecules. They're helping reactions take place so that we function properly. So the way an enzyme works is it has what's called an active site, and this is where a reaction can take place. So our reactant will be called a substrate, and it's going to deposit itself onto the enzyme, And then the enzyme can just kind of hold that reactant in place and help it react faster. And this can occur in a lot of different ways. But at the end, the enzyme will release the products, and then the enzyme can be used for another reaction. So again, the enzyme isn't used up during the reaction. So one example is the enzyme alcohol dehydrogenase. And alcohol dehydrogenase helps break down alcohol. But if you lack the enzyme, or if the enzyme doesn't work properly, then that can slow down the metabolism of alcohol. So enzymes are great, but sometimes just based on our biology, we might lack a particular enzyme, or maybe our enzymes don't work as well. So in general, though, they're a catalyst that should help speed up a reaction. Now, there are a couple of different explanations for how catalysts work, and it kind of depends on the type of catalyst you're using. But one explanation is that a catalyst provides an alternate reaction pathway that requires less activation energy than the normal pathway. So down below we have another energy diagram, and again we have reactants and products. And this is an exothermic reaction because the reactants are higher in energy than the products. So if we have an uncatalyzed reaction, so there's no catalyst present, then the activation energy is quite high. However, if we add a catalyst, that lowers the energy required for the reaction to occur. Now, another explanation proposes that solid catalysts provide a surface on which reactant molecules will adsorb, and they'll kind of place themselves so that they're favorably oriented towards each other. So for instance, let's say we were using a solid catalyst with our carbon monoxide and oxygen example from earlier. The solid catalyst would help the carbon monoxide and the oxygen properly face each other so that the carbon is lined up with the oxygen. And then any adsorbed molecules with favorable orientations that are located really close to each other will react. So there are a lot of different ways that we can speed up a reaction. So we just saw we could increase the concentration of the reactants, we could increase the temperature of the reaction mixture, and we can also add a catalyst. Now, one way that we could slow down a reaction is using what's called an inhibitor. And an inhibitor is almost the opposite of a catalyst. So, for example, let's say you accidentally ingested a poisonous substance. We would want to slow down that reaction or stop it completely by using something that inhibits the reaction of the poison. So maybe there's a medicine that we can use to slow down that process. And we're not going to focus too much on inhibitors in this class, but I'm sure you'll learn more about them later on. All right, so I think we'll end here today. Next time we're going to talk about chemical equilibrium. So we're going to talk about reactions that have a forward direction and a reverse direction. So the reaction can go back and forth. So I will see you in the next video.